Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on different types of crystals. Previously, we discussed molecular orbital theory, which sounds much more complicated than it actually is. We learned that when atoms bond to form molecules, their atomic orbitals combine to create molecular orbitals. We also learned that we can describe the orbitals of a molecule using a molecular orbital diagram. In today's lesson, we will learn what crystals are. We will list the 4 types of crystalline solids. We will discuss the properties of each, and we will look at some examples. We are also going to discuss the types of attractive forces that exist within each type of crystalline solid. Students, we have a lot to cover in this lesson, so let us begin. A crystal is a piece of solid substance that has a plane surface, sharp edges, and a regular geometric shape. The atoms, ions, or molecules that make up a crystal are arranged in a regular, repeating manner. These particles extend in 3 dimensions throughout the crystal. An essential feature of a crystal is that its entire structure can be determined by looking at just a tiny piece of it. Some solids, such as glass, lack this long-range order. These solids are said to be amorphous. The structural components of such solids occur at random positions, and, like water, they have no ordered pattern. There are 4 important classes of crystalline solids: ionic crystals, molecular crystals, covalent network crystals, and metallic crystals. Let us discuss each of these in turn. Ionic crystals are made up of both positive and negative ions. As a result, the interparticle forces, or ionic bonds, are a lot stronger than the van der Waals forces that exist in molecular solids. In order to maximize the attractions, the cations are surrounded by as many anions as possible, and vice versa. The strong interionic forces within ionic crystals create a high lattice energy, which affects the properties of these solids. Crystalline ionic solids are often brittle non-conductors of electricity. However, molten crystals can be good conductors. Crystalline ionic solids often have high melting points as well. Some common examples of ionic solids include sodium chloride, or table salt, saltpeter, washing soda, and blackboard chalk. Students, this video shows the arrangement of a sodium chloride crystal lattice. It also shows what happens to this lattice if the size of the solid is increased. Students, after watching this video, describe the features of this sodium chloride lattice that make it a crystal.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. I hope you enjoyed that activity. The sodium chloride lattice is made up of ions that are assembled in a regular and repeating manner. They also extend into 3 dimensions throughout the solid. Every tiny portion of the sodium chloride lattice looks identical. Therefore, the entire structure can be determined from just a small portion of it. All of these features show that the sodium chloride lattice is a crystal. Let us move on to discuss molecular crystals. Molecular solids are made up of molecules. Organic compounds and simple inorganic compounds are often molecular solids. Molecular solids contain different combinations of dipole-dipole, dispersion, and hydrogen bonding forces. Dispersion forces often act in non-polar substances. Thus, as the molar mass of these substances increases, so too do their melting points. In polar molecules, dipole-dipole and hydrogen bonding dominate. However, the forces in these substances are quite weak, so their melting points are lower than those of ionic, metallic, and network covalent solids. Molecular crystals are often brittle, transparent, non-conductors of heat and electricity. Some common examples include sugar, glucose, aspirin, and dry ice, which is solid carbon dioxide. In covalent network crystals, strong covalent bonds link atoms together throughout a network of covalent solid. In a covalent network solid, the whole crystal is one giant molecule. Since there is such strong bonding in these substances, they have very high melting and boiling points. However, their conductivity and their degree of hardness depends on the nature of their bonding. Graphite, diamond, and quartz are all examples of covalent network crystal. While these two substances have the same composition, they have very different properties. Graphite occurs as stacked flat sheets of hexagonal carbon rings. It has a strong sigma bond framework and delocalized pi electrons throughout the sheet. These delocalized electrons make graphite a good conductor of electricity. Within diamond, each carbon atom is bonded to 4 other carbon atoms in a giant tetrahedral structure. The strong single bonds that connect the carbon atoms in diamond make it the hardest known substance. Diamond does not conduct electricity due to its localized bonding electrons. Examples of covalent network solid include quartz. The identical metal atoms that make up metallic crystals are held together by strong metallic bonding. Metals are electrically and thermally conductive, they are malleable and ductile, and they have luster. Metals have a wide range of melting points and hardness. These properties depend upon the packing efficiency of the crystal structure, as well as the number of valence electrons that are available for bonding. Some common examples of metals are copper, gold, silver, aluminium, and iron. Students, we have time for one last activity. Please list the attractive forces that exist within each type of crystal.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, students. I am sure you found this activity to be quite simple. Ionic crystals contain ionic bonding. Molecular crystals can contain hydrogen bonding, dipole-dipole, or London dispersion forces. Covalent network crystals contain covalent bonding. Finally, metallic crystals contain metallic bonding. Today, we learned about 4 important types of crystals, including ionic crystals, molecular crystals, covalent network crystals, and metallic crystals. Our next lesson will be a review of this unit. This is all for our lesson. Until next time, thank you, teacher. Thank you, students.